Hello, and thank you so much for tuning into this video. This video is a recording of a conference or of slides that I've presented in September this year at the Symposium on Thermoacoustics in Combustion, SoTiC 2025 in Trondheim. The topic of this talk is hard-constrained neural networks for the reconstruction of acoustic waves from pressure data. And this work was mainly carried out by Lynn Tees, myself, and supervised by my supervisor, Camilo Silva. We are all working in the Thermo-Fluid dynamics group at the Technical University of Munich. And with that out of the way, my face will disappear for the remainder of this talk, and I hope you enjoy the slides from now on. Generally, in thermoacoustics, an accurate acoustic field reconstruction is highly desirable. Why? As you can see here on the right, when we have a typical test rig, an experimental test setup, we may be able to place some microphones in the close vicinity of the combustor, but not everywhere, not only due to costs, but also due to spatial constraints. But what we want to have is the most accurate representation of the acoustic field inside that test section or the entire setup, because any design decision that we as engineers make impacts the acoustic impedance of the system and therefore impacts the general behavior of the system. And the only way to quantify this behavior is via acoustic data in the first place. Furthermore, acoustic data allows us to identify malfunctioning operating conditions, or generally speaking, areas where problems may arise or may originate from. So, going back to the question, how can we infer the acoustic field from this limited amount of data that we have with the highest accuracy possible? Okay, with the multi-microphone method, we have access to a very established and very well understood method that relies on an axial array of sensors for the reconstruction of the acoustic field. The idea is we place at least 3 or more sensors in such an axial array as depicted here in the figure, and then we measure the pressure fluctuations in space and in time. What we can then do is we can use the one-dimensional wave equation, as shown in a second, to correlate the measurements and thus reconstruct the entire field also in between the data points and in between different time sampling points. It's a very popular technique, not only in thermoacoustics, but especially in thermoacoustics. However, it generally uses the assumption of a constant speed of sound. It doesn't have to, but it's a very common assumption. And typically it is combined with external acoustic forcing at specific frequencies only to get rid of any spurious frequency contribution. So, just discussing the ansatz real quick, the underlying one, we take the 1D acoustic wave equation as depicted here on the top of the slide. And if the speed of sound is constant, we can express the acoustic pressure, so the pressure fluctuation as function of x and t, as a simple superposition of multiples of forwards and backwards traveling waves. This is a very popular solution to the 1D acoustic wave equation. The qualitative solution is shown in the figure as orange and blue traveling waves. Now we can take this solution and re-implement it in the form of a neural network. So basically just recreating the multi-microphone method ansatz as a neural network. The neural network architecture is shown here. We use in the input layer just position x and time t. We multiply each of these inputs either by the spatial wave number k, which is just the temporal frequency omega divided by the speed of sound, or by, well, the temporal frequency omega itself. This is then fed into the first and only hidden layer, which contains an activation function. In this case, it's a harmonic activation function, so the sine of whatever is the input to the cell. It can contain a bias, which accounts for phase shifts, and it's then multiplied by some factor, which corresponds to the amplitude of the corresponding wave, summed up via a linear superposition. And this then yields YA, which is simply the forward traveling wave amplitude of x and of t. We obtain the total solution from superposition. So as already presented, the solution is just the superposition of a forward and backward traveling wave. If we implement each wave solution as its own neural network, we can, well, just superpose them to get the final output. This is shown in the figure on the right. Keep in mind, the neurons that we use here use an harmonic activation function, and we can leverage the physical knowledge that we have to reduce the number of network parameters. Because of course we know that for a given forwards traveling wave, the corresponding backwards traveling wave has the same spatial wave number k and the same temporal frequency omega. So these parameters can be shared between each neural network, NN forward and NN backwards, to limit or to reduce the amount of parameters that we actually need to train. So far, we just recreated the multi-microphone method as an N architecture, which per se does not gain or give us any advantage. However, the question is now, can we leverage the nonlinear modeling power of neural networks for the case where the speed of sound is no longer constant, which is commonly not the case in a thermoacoustic setup where we have strong temperature, dust density, and also speed of sound gradients. Okay, before we can go here, we first of all have to revisit our underlying ansatz for the case where C is no longer just constant, but actually a function of X. In this case, the amplitude of each wave, so the amplitude of each forward and also of each backward traveling wave, is no longer constant, but becomes a function of space itself. As the speed of sound is now also a function of X, the product of spatial wave number k, which is just omega divided by C, times X, becomes a general nonlinear function. The new ansatz now, and we only show the forward solution approach, but it works in a similar manner for the backwards solution, is now P prime of f of x and t. So the acoustic pressure that corresponds to the forward traveling wave is now just an amplitude that depends on x and is no longer constant, times sine of omega t minus this nonlinear function that depends on x. This nonlinear function now swallows this dependency of speed of sound on x. And you can see here that this nonlinear function phi of x is basically just omega times a function f of x. If we insert this ansatz into the wave equation and consider only dominant terms of order omega squared, we can show that the evolution of amplitude a as a function of x adheres to this law where we have a constant amplitude that comes from a boundary condition divided by the square root of the speed of sound, depending on x now, and this function f of x that we use inside the harmonic function is just the integral from 0 up to current position x over 1 over c of x. Note also that the phase shift is not really relevant for this derivation, but it is considered in all solutions that we present in the following slides. Okay, so the question now is we have this new ansatz, and most crucially what is happening here is that basically this f of x is swallowing the dependence of the solution on c of x, and instead of learning c of x directly, we learn f of x. Now, how can we learn f of x? As I said, we want to leverage the nonlinear modeling capacity of neural networks. And in order to do so, we can just take the neural network that we already built, which was just re-implementing the multi-microphone method. And you can see this here in blue on the right side. And instead of giving it as input x, so just the coordinate as we've done it earlier, we now give it as input this function f of x. And this function f of x is the output of another neural network which sees x as input. So what we have is we have a neural network that predicts f of x given x. So basically it predicts the variable speed of sound c of x. And this neural network in orange here relies on standard nonlinear leaky ReLU activation functions, so no longer harmonic activation functions. And the approximation of f of x is then given to our already known, already presented neural network that just re-implements the multi-microphone method. So strictly speaking, what you could do is you could, of course, also just use the multi-microphone method and upstream of it place a neural network. But combining everything or writing everything as one large single neural network just allows to train everything more efficiently or more easily. Now, in terms of training data, we rely on noisy broadband pressure data, and we do not, this is important, provide any information about the acoustic velocity. We just use some artificial training data for the presentation here, which is generated using a numerical solver for acoustics taken from Yao and Silva 2024. We apply a broadband forcing at the inlet, so no monofrequent forcing, but broadband. We add some white noise to it to achieve a signal-to-noise ratio of roughly 7. And then we vary the temperature profile across a length of 1 meter from 1500 Kelvin to 700 Kelvin, which we do to induce a variable speed of sound. We then provide data at 5 distinct microphone positions equally spaced across the channel, and we do not provide any temperature data or acoustic velocity data, only pressure data. So in terms of a cost function or a loss function that we need to, well, adapt the weights of each neural network, we leverage a Fourier-like transform, which allows us to learn frequencies and phase shifts more efficiently. So basically, we use a mean squared error cost formulation that allows us to mainly learn this spatial dependency of the amplitude, so A of x and B of x. This is the first part in the loss function, which is scaled by some coefficient alpha. And then we use a formulation, as I said already, analogous to the Fourier transform, which allows us to learn the frequencies omega I, as well as phase shifts phi and theta I more efficiently. Why do we need to do this? The problem is whenever you use harmonic activation functions, it can be shown that your network is super prone to getting stuck in local minima just due to the nature of the periodicity of these harmonic activation functions. And to avoid that, we use this Fourier-like transform, which clearly favors when the network hits the correct frequency and phase shift. So let's have a look at the pressure field data, which is the data on which we train on. So we can see here that the pressure field data is recovered very well with less than 10% maximum error, and the mean error is around 2%. So again, we provide pressure data only at these reference positions, which are highlighted in the bottom plot in red. And then the network predicts the entire pressure evolution across the entire channel, as well as across a vast range of time. We just show a selected range of 24 milliseconds here, and we can see that the predicted pressure evolution matches the reference pressure evolution very good. Note that the reference pressure evolution looks a bit grainy here in this picture, but this comes from the fact that we apply noise to it. Given now that we have the pressure available in the form of a forward and backward traveling wave, as well as density and speed of sound, and the density is just calculated via the relation here on the top right, so we take the mean pressure and the speed of sound squared. Note that we thus do not rely on any quantity that cannot be either looked up in the case of gas properties or fluid properties, or just be taken out straight off the neural network itself. Doing so, we can reconstruct the acoustic field, and again, the match is very good. Maximum error is still around 10%, and mean error is in the range of 3%. The interesting question now is, are we also able to recover the underlying profile for the speed of sound C of x? First of all, we have to consider what the network was actually predicting, and the network was not predicting C of x, but the function f of x. So if you recall our ansatz, we have this phi of x, and phi of x is just omega times f of x, and f of x is what the neural network is actually learning. So if we compare the network output for f of x with the analytical reference, we can see a very nice match over the entire length of the duct. So focusing now on the actual speed of sound, we have to take the derivative of f of x. And here we can see that, well, the general shape of the profile is recovered nicely. So we have a qualitative recovery. We are lacking the correct slope to some extent, and thus have some mismatches towards the beginning and at the beginning and towards the end of the channel. Where does this come from? In our opinion, this simply stems from the fact that the neural network is not learning C of x directly, but, well, due to the ansatz itself that we chose, the network is learning f of x. And f of x represents the integral over C of x. And it's known that the integral or integration in general is able to swallow small errors, where taking the derivative amplifies small errors. So if we learn something up to a high degree, as shown one slide earlier, but then take the derivative of it, the errors can amplify. So what have we shown so far? We demonstrated that we can reconstruct the acoustic pressure field under the presence of noise. So signal to noise ratio was in the ballpark of 7. we can reconstruct the acoustic velocity field from information that is contained only inside the trained neural network, so no additional acoustic field data or temperature data is necessary. And we are able to qualitatively recover the spatially dependent speed of sound. And as I already said, we used broadband acoustic pressure signals at only a few locations and not the common approach of using monofrequent signals. Okay, so what is left to be done in the future? Future work should employ signals from experimental test rigs and also consider in situ combustion chambers. And here it would be especially interesting to infer the acoustic impedance of components or of boundary conditions at locations where no measurement equipment is installed due to possibly spatial constraints or cost constraints. It would also be very interesting to conduct a sensitivity analysis with regards to the number of microphones for a given case. How does the sensitivity change when we increase the noise, decrease the noise, change the temperature profile to more complex temperature profiles? So there's still a lot of investigations that can be done. Nevertheless, we are convinced that this work provides a solid first step towards a more potent approach of recovering complex acoustic fields for varying speed of sounds. So thank you very much, and I hope to see you in another video in the future. Goodbye.